One of the main things that we've done with the dot product in Rn is used it to come up with an orthonormal basis for Rn. We can turn any basis in Rn into an orthonormal basis just by doing the Gram-Schmidt process. Well, if you look at the Gram-Schmidt process, it actually, the formulas in the Gram-Schmidt process only depend on the properties of the dot product that we require of any inner product. So for that reason, we can use the Gram-Schmidt process to come up with an orthonormal basis for any basis in an inner product space. So for example, in P1, this, 1 and x, this is a basis. But we can regard P1 as an inner product space by using the inner product that comes from continuous functions from 0 to 1. So the inner product of two polynomials will be the integral from 0 to 1 of p of x times q of x. Q. Okay, so what we might want to do is come up with not just a basis for P1, but an orthonormal basis. Of course, the reason why it's nice to have an orthonormal basis for P1 is exactly the same as why it's nice to have an orthonormal basis for Rn. In Rn, it's very easy to compute representations or projections using an orthonormal basis. And exactly the same thing is true of any other inner product space. So you can imagine if you were going to do a bunch of projection calculations in P1, you'd really like to have an orthonormal basis. So let's work out an orthonormal basis. So to do Gram-Schmidt, remember what we need to do is, so the first element in the basis you leave alone, right? And then there's more than one way to do Gram-Schmidt. The general idea is always the same. You just take your vector and subtract off projections onto earlier basis vectors, but the details of like when you normalize things depends on who you're talking to. Fortunately, we don't need to worry about when to normalize this first basis element, 1, because its norm is actually 1. So, right, if we just calculate the inner product of 1 with itself, that's the integral from 0 to 1 of 1 times 1, but that's 1. So the norm of the basis element 1 is 1. In other words, 1 is already a unit vector. Okay, so for our second basis element, so I guess that's going to be our first basis element, the polynomial 1. So for our second basis element, for our second basis element for the orthonormal basis that we're producing, we take our second basis element for the basis that we started with, and then subtract off the projection onto the first basis element of our second basis element, right? So, right, this is exactly the same formula as Gram-Schmidt in Rn, right? It's just that our vectors aren't vectors in Rn, they're polynomials of degree less than or equal to 1. Okay, so this is x minus, so what is this projection? Well, again, the formula for a projection is exactly the same in an inner product space as it is in Rn. So it's the inner product of x and 1 divided by the magnitude of, the norm of 1 times the vector 1. Of course, we know that the norm of 1 is 1, so we don't need to calculate this again. But we're going to need to calculate this inner product of x with 1. So that's inner product of x with 1 is the integral from 0 to 1 of x times 1. So that's, right, 1/2 x squared from 0 to 1. That's a half. Okay, so this beta 2 that we're calculating is x minus, right, this right here we now know is a half, so x minus 1/2, right, this is the scalar 1/2 times the polynomial 1, but that's the polynomial x minus a half. Okay, Now we need to, so this, remember, when you do this calculation in Graham-Schmidt, the result might not be a unit vector. It definitely is orthogonal to the previous vectors in your basis. I won't check that, but it is. These two are orthogonal. But this vector might not be unit length. So we need to calculate its norm. So x minus a half and x minus a half. So this is integral from 0 to 1 of x minus a half times x minus a half. So that's x minus a half squared dx. So this is integral from 0 to 1 of x squared minus x plus a quarter, I guess. So this is 1/3 x cubed minus 1/2 x squared plus 1/4x. And we need to evaluate at 0 and 1, and so we get 1/3 minus a half plus a quarter. So 1/3 minus a quarter, that's a 12th, I think, right? Yeah, 12th. Okay, so that means that the norm of x minus a half is the square root of this. And so the second element in our orthonormal basis is going to be x minus a half divided by its own norm. So the reciprocal of this, which is the square root of 12, apparently. Okay. So our orthonormal basis is 1 comma square root of 12 times x minus a half. Okay, and so there's an orthonormal basis for, for P1 as a subspace of the inner product space C from 0 to 1.